this video, we're talking about 45, 45, 90 triangles. And when we say a 45, 45, 90 triangle, what we're talking about is a triangle that has this set of three interior angles. So two of its interior angles have a 45-degree measure, and the third interior angle has a 90-degree measure. So the first thing you can say right off the bat is because there's a 90-degree measure in the triangle, it is going to be a right triangle. So if we look at this first example here, we have a right triangle, so this is a 90-degree angle, and then two 45-degree angles, so this is the special case of a 45, 45, 90 triangle. And the reason that we talk about this specific type of triangle as being special as opposed to just being like any other right triangle is because a 45, 45, 90 triangle is exactly half of a square. So if you take this figure and you just complete the square of it, right? So we have, this is actually the other half of a square, right? We're going to notice a couple of things. First of all, we're dealing with a square, which means we're going to have four 90-degree angles at the corners of the square. So we have these 90-degree angles, this one that we already knew that's in our triangle, and this one on the opposite side of the square. We're also going to have 90-degree angles at these corners, but of course when we cut the square exactly in half along its diagonal, we're going to have 45 degrees on one side of the diagonal and 45 degrees on the other side of the diagonal, summing to a total of 90 degrees. And so you can see 90 degrees in this corner and 90 degrees in this corner, and so we notice that this is a square. So a 45, 45, 90 triangle is a special case because it's exactly half of the square, it's just everything on one side of the diagonal of the square. Now the reason it's useful to know about this special 45, 45, 90 triangle is because if we need to find the length of the diagonal of square and we happen to know one of its side lengths, which is going to be the same for all four sides because it's a square, all we need to do is multiply the side length by the square root of 2 to get the length of the diagonal. And that's because of the Pythagorean theorem. So if you can imagine if we have this square here and we go ahead and say that the length of one side of the square is s for the side, then the length of all four sides is going to be s, and the length of the diagonal is just going to be square root of 2 times s. That'll always be the length of the diagonal because of the Pythagorean theorem. So let's go ahead and take a look at why that works. So in this first problem here related to this figure, we've been told if a is equal to 6, so this side length over here is 6, then find the length of b and find the length of c. Well, remember, a 45, 45, 90 triangle is always one half of a square, which means that the two legs of the triangle are always going to be equal because a square has four equal sides. So the side length for A is always going to be equal to the side length for B, so we know right away that B is going to be 6. Of course, then what we can say for this triangle is that because we have two opposite sides that have an equal length, this is, of course, an isosceles triangle, which should make sense to us because by the isosceles triangle theorem, we have these two opposite sides that are equal, which means the opposite angles are also going to be equal. And of course, in this case, they are. The angle opposite of A is this angle right here, and that's 45 degrees. The angle opposite side B is this angle right here, and it's also 45 degrees. And as we know with an isosceles triangle, when we have opposite sides that are equal, the triangle's isosceles, and that means that the angles opposite of those sides are also going to be equal, and we can see that we have 45 degrees and 45 degrees, so we have equal angles. So that's another special thing about a 45, 45, 90 triangle. It is an isosceles triangle, and we can use the isosceles triangle theorem and the converse of the isosceles triangle theorem on this triangle. So we know that if A is equal to 6, then B is equal to 6. Well, what about side length C? Of course, C is the hypotenuse of this triangle, and because we're dealing with a right triangle, because this is, of course, 90 degrees, we can use the Pythagorean theorem, which remember tells us that A squared plus b squared is equal to c squared. In other words, a and b are the lengths of the legs of the triangle, c is the length of the hypotenuse of the triangle, and in this case here we had a and b, we know that they're both 6, we're looking for c, the hypotenuse of the triangle. Well, to find c, we could use the Pythagorean theorem and say a squared plus b squared equals c squared. So in our case, a is equal to 6 and b is equal to 6, so we could say 6 squared plus 6 squared is equal to c squared. We'd get 36 plus 36 is equal to c squared. 72 is equal to c squared. And if we take the square root of both sides, we're going to get square root of 72 is equal to c. Square root of 72, remember, we have the square root of 36 times 2, so we can say the square root of 36 is 6, and so this simplifies to 6 times the square root of 2 is equal to c. So this is using the Pythagorean theorem to find the length of the hypotenuse. However, remember this formula here, which told us that in the special case of a 45, 45, 90 triangle, we can use this formula to find the length of the hypotenuse, which remember is also the length of the diagonal of this square, just by taking one of the sides of the triangle and multiplying it by the square root of 2. We know that a is 6, so if we put a into this formula 6 here, we can say c is equal to 6 times the square root of 2, and we get 6 times the square root of 2. And notice that's exactly the same answer we got here using the Pythagorean theorem. So you can always fall back on the Pythagorean theorem if you don't remember this formula specifically. But this is a shortcut that will work all the time whenever you're dealing with the specific case of a 45, 45, 90 triangle. So we can say that c is 6 times the square root of 2, or just either of these side lengths, 6 here, times the square root of 2. Now what about if we're working the opposite way? We've been given the measurement c is equal to 6, so in this case we're saying the hypotenuse c is equal to 6, and we want to find the lengths of both of these sides. Well, first of all, we know a and b are going to be the same because this is an isosceles triangle, and therefore a and b are going to have an equal length. Well, if we go ahead and solve this formula right here, we could use the Pythagorean theorem, but if we solve this formula right here for a, one of the side lengths, we get a is equal to c divided by the square root of 2. So we already know c is equal to 6, so that means a is going to be 6 divided by the square root of 2. If we want to rationalize the denominator here and multiply by root 2 over root 2, we're going to end up getting 6 square root of 2, all divided by square root of 2 times square root of 2, or just 2. And of course then we can factor a 2 out of the numerator and denominator. This 2 will cancel in the denominator, leaving us with just 1. 6 divided by 2 will give us 3, so we're left with 3 square root of 2. Of course, because a and b have equal length, we know then right away that b is also going to be equal to 3 square root of 2. But if you wanted to prove that with the Pythagorean theorem, since we know that a and b have an equal length, we can say a equals b in this case. And so this is really just the same as a squared plus a squared is equal to c squared, or 2a squared is equal to c squared. And we could go ahead and plug in c equals 6, and we would get 2a squared is equal to 6 squared, or a squared is equal to 36 divided by 2, or 18. And then when we take the square root of both sides, we get a is equal to the square root of 18, or the square root of 9 times 2. Square root of 9 is 3, so we get a is equal to 3 times the square root of 2, which notice is the same thing that we got here using the formula c equals square root of 2 times a when we manipulated it to solve for a. So again, you can always fall back on the Pythagorean theorem, but in the specific case of a 45, 45, 90, you can always use this formula c equals square root of 2 times the side length. In other words, the diagonal of a square, or the hypotenuse of a 45, 45, 90 triangle, is always going to be the square root of 2 times the length of one of the sides, or the square root of 2 times the length of one of the legs. It's all the same thing. So what about in a question like this? Which of these represents a 45, 45, 90 triangle? And we've been given the 3 side lengths of a triangle. So we know that the 3 sides of the triangle are 4, 4, and 4 times the square root of 2. Well, remember in a 45, 45, 90 triangle, it's always isosceles, which means that 2 of the sides have to have the same length. So what we can identify right away is that these 2 sides here have the same length. They're both equal to 4, so they must be the legs of the triangle. The third side that's unequal has to be the hypotenuse, and it has to be this value here times the square root of 2, and in fact it is. We multiply 4 by the square root of 2, and we get 4 times the square root of 2, and therefore we can say that these 3 side lengths would in fact represent a 45, 45, 90 triangle. What about this example here? Well, we notice right away that we have 2 equal side lengths, 3 square root of 2 and 3 square root of 2. So we know that the triangle is isosceles, and that's the first thing we want to look for. We've got equal sides here. This third side, therefore, must be the hypotenuse, and it has to be one of these side lengths times the square root of 2. So if we take 3 square root of 2 and we multiply it by square root of 2, what we're going to get is 3 times square root of 2 times square root of 2 is 2. So we get 3 times 2, and we get 6. And because we get 6 here, which is the third side length, we can say that this also represents a 45, 45, 90. In the last example here, we can see that we have two equal side lengths, 5 root 2 and 5 root 2, so these must be the legs of the isosceles triangle. The third side has to be the hypotenuse, and it has to be this length here times the square root of 2. So if we take 5 square root of 2 and we multiply it by square root of 2, what we're going to get is 5 times square root of 2 times square root of 2 is 2, and we get 10. But 10 does not equal this third side length of 5, so this measurement here, these three side lengths, do not represent a 45, 45, 90 triangle. This value here for the hypotenuse would have to be 10 if these are the lengths of the legs of the triangle in order for this to represent a 45, 45, 90. And that's how you can use what we know about 45, 45, 90 triangles to solve problems like these ones.